Alright, hello and welcome to your next lecture. This is an exciting one because in this lecture we start a long line of data structures slash abstract data types, and this first one is called list. So I don't know why I can't click at the moment. That's probably why. So lists are very similar to arrays or vectors, but they differ where it counts, and so we'll talk about that. And yeah, I'm just excited. I'm excited for you. Yeah, so let's get right on into it with linked lists, and those are the data structure behind the list abstract data type, usually at least. Now, this is a data structure. Let's just say that. And you don't have to implement the list ADT using linked lists, but you probably should usually. It's the best thing to put inside a list. All right, so now let's kind of build up the idea of a linked list very, very slowly. I know I've shown you pictures of this, just hinting at it, and I know you're reading about this in your book, but let's just start from first principles. So we're trying to discover why we might hate arrays for some things. All right, so here's our favorite array. It's got some stuff in it. It's got some empty space that we haven't filled yet, perhaps. What are the pros and cons of arrays slash vectors? And I really do encourage you to pause this video and think about that. What in the world is so good about an array? What's so bad about it? Well, actually, it'd probably be easier to type, wouldn't it? I would like that. So one thing that's really nice about an array is that all your stuff is sitting right next to itself in memory. Contiguous, in memory, and you can immediately get to some place, okay? So you can get somewhere really fast. And any element at a certain index, for example, I don't know, 0, 1, 2, 3, 4, 5, 6, any of those indices, you can get to super quickly by just doing some deep down in your CPU, some address arithmetic, okay? Yeah, so that's a good starting point for pros for arrays. What about some cons? What do you think? Well, the first thing that comes to mind is, well, you're kind of stuck with the size you get, at least for arrays. Size you get. So you cannot make it any bigger. You do have a pushback for vector, but we're kind of talking about both right now. And for both arrays and vectors, it's also super difficult to add something in the middle. Let's say I wanted to put 3.5 in between 3 and 4, and I have some room. What you have to do is shuffle everything. You got to move over everything by an index. And this really sucks when you want to put something at the very beginning of a vector or an array that's already got stuff inside. So you got to start shuffling them all over to make space. And this just became an O of n operation to add something. You see that? A linear time operation because you have to move everything in the array. That sucks. The end is easy if you have space. Just put something there. So hopefully you understand these pros and cons, and maybe you've ran up against them in a previous life. So that's where we're going. That's where we're starting. Now let me show you what a linked list looks like when we draw it. So remember array? This is a linked list. It's got elements. It's got data. So but it's just stored in a different way. So this is a linked list, and it holds 1, 2, and 3 in that order. So if I was going to use a Python style list, I'd write it like that, in that order. Okay, so it's 1, then 2, then 3. This is what a linked list looks like. Okay, and there's pointers everywhere. So this is a pointer. This is a first pointer. This is the last pointer. And this is a single element of our linked list, and it's called a node. Okay? So this right here, or maybe we'll talk about this one. It's called a node. And each node, I'll draw it like this, it has a data element. That's usually the first thing that I'll draw. And then it has a next element, okay? And the data holds the data, like whatever it was. Maybe it's 42, maybe it was like a string. Could be anything that you put in this box. But the next is always a pointer, okay? So this is a pointer. So it's some kind of address, okay? So it holds its data, but also how to get to the next place in the list, okay? All right, that is the idea with a linked list, and it is a competitor to an array. So you kind of have to use these first and last pointers to move around, though. So let's see here. If you wanted to get to the 2 node, you had to start from the first pointer, which would bring you here. And then you need to follow the next pointer once you're here. You follow this pointer to get to here. Okay, and I'll show you this in code in just a second, don't worry. So going back to the cons of vectors, we can put all this stuff on the heap. Like, we can just randomly make a brand new node, shiny on the heap, and we don't have to worry about the issue with arrays where we're stuck with the size we get. We can always make a new node on the heap, okay? New nodes usually made on the heap, which is super nice. And then also, it's really easy to add stuff to the beginning, to the middle, and to the end. If I wanted to add a new node right here, before to first, I just have to swap first around, make a new node on the heap, make this next pointer go there, and first point there. You see that? That's beautiful. And then, one thing that you do have to watch out for is once you get to the very end of the list, the last element, that is highlighted with a null pointer, and I'll draw it like this little slash. Okay, this is a null next pointer. Okay, and in C++ you can use 0, you can use capital null, but I will prefer the C++ 11 and later version of nullptr to mean null. Okay, that's what this holds. Holds like the 0 address. Nothing there. Nowhere. There is no next place in this list. It's the end. Okay, so it marks the end. Yeah, that's the beauty of linked lists. They solve a few problems. All right, so let's come at this slowly. Let's make the list 1 and then 2 in code. Okay, so I'm gonna have a first pointer, I'm gonna have a last pointer to the first node to the last node. And remember, this whole thing is a node. Normally, when I draw things that have things inside of them, it'd be like, here's my node n, here's its data, here's its next. But just to save us a lot of writing, save me a lot of writing, we just draw it like this, kind of like an array notation. But we know that the first thing is the data, the second thing is the next pointer. Okay? That's the idea. So I'm kind of making this faster. Whee! So it just looks like this. Boop. 42, null, 42, and a slash. Yeah? So if we want to store a list, we have to somehow make nodes. So what does a node look like inside of code? Okay? How are we going to make a node data structure? And that word should be extra helpful. We can make a struct to hold those things, the data and the next, in one place. Okay, so we can say struct node and some braces, and always that semicolon. And then we can give the stuff that's inside. There's always a data element, and there's always a next pointer. So we need a data, and we need a next. But what are the types of these things? What goes here? Take a minute to think about that. At least for this kind of list, remember we can have a list with anything inside. We could have strings for all we care. Hi. But in this one I've used numbers. So we can say int data. That's the type of stuff that goes in the data field of a node. Okay? And then the next, well, it's a pointer. We know that. What's it a pointer to? It's a pointer to... Wait, it's a pointer to another node. What? Now this is interesting. Let's highlight this. I'm defining a data structure called node, and I am defining it to have nodes inside of it. This is a recursive type. It's beautiful. So that shouldn't scare you or anything, just trying to point that out. It's fun. We're now using recursion inside of a data type instead of like a function. Isn't that cool? So yeah, a node holds its data, and then it also holds a pointer to the next thing in that list, which is another node. Okay, so node pointer. Yeah, that's all it means. So let's make the list now 1, 2 in source code, in C++. And yeah, that's what I want to do. So here's how we should do it. Let's get into our folder. Let's make a directory for lec09, and let's go inside of that. Alright, so there's nothing there. I'm in my lecture 9 folder. How do I want to call this? 12.cpp? How about that? Alright, I'm just going to be lazy and make this all in one file. So we need our node data structure. Alright, so there it is. And it's going to have int data and node star next. Okay, so this linked list holds int data. It can hold data of any type, but we're going to say ints, and this is how it gets to the next place. It's like it's playing telephone. It's like, I need the 6th element, so you're going to follow 5 next pointers. Alright, and then down here in main, this is trying to make it all pretty for me. I don't want it to do that yet. Down here in main, what we can do is start making our nodes. Okay, normally we make them on the heap, and so I'll just start us out there. But notice that you can do something like this. You can always say node n. This makes a brand new node. It's on the stack. Not a problem to do this, but we tend to make our nodes on the heap instead. Okay, that's all. Yeah. And the reason for that is because we want to add stuff to our lists dynamically. So I'm gonna use pointers instead. So remember what we need. Yeah. We need a first pointer, we need a last pointer, and we need 2 nodes. Okay? Technically, we only need first and last, but this is how it's going to work in real life. So node star, here's the node that will hold the 1. I'll call it 1, equals new node. Yes? And then node star 2 equals new node. And the 1 node, well, I'll just make them both. So now I have them. So I've essentially made this so far. I've made 1. Well, it's technically a pointer to the heap. Let me make a new slide. So I've made my 1, which is, this is all stuff on the stack at the moment. I don't want any design ideas. And then I have the heap. So I've made 1. It's a node. No, sorry. I'm so sorry. 1 is a pointer to a place on the heap that is a node. Okay? And right now it's got everything undefined because we just declared it and didn't initialize anything. And same for 2. Okay? These are just pointers to the heap that are nodes, that hold nodes. Okay? And again, it's undefined. But we want to set up this. Boop, boop, 1, 2. Yeah? So let's start there. So 1, and remember we can't use the dot, we can't say dot data equals 1, because 1 is just a pointer. We have to follow the pointer to get the actual node. So I have to say either star1 dot data equals 1, or alternatively, one arrow something. That is the difference. Okay, so these are equivalent. Remember the arrow, it'll save you a lot of typing. So one's data is 1, one's next is a pointer to the next node in the list, which, oh man, I'm storing inside of this 2 variable. Okay? And then similar stuff happens for 2. 2's data will hold 2, and 2's next, what's the next thing in the list after the 2 node? Nothing, because it's the end. Null pointer. Okay? Yeah. So this is 1, 2 using nodes, and if we want to include our first and last, we'll say node star first. What's the first thing? Well, it should be the 1 node. Yeah. So now I'll have first and last, and they should go like this. Technically I didn't need them because I had 1 and 2, but that's okay. Okay, so that's the idea. We have first and last now, and all those things are all hooked up properly. Okay, that's our linked list. We made 1 and 2. Isn't that cool? Okay, let's move on. Let's make a longer list and iterate through that. All right, so we had 1, 2. We had first, and that pointed to the 1 node. Then we had a 2 node. Maybe let's make 1, 2, 3, and then iterate through that. Yeah. So let's do this. How are we going to iterate through this list? First of all, there's no indices. We can't say like, I don't know, first dot at I. That is a no-go. Okay? What are we gonna do? I wanted red. Whatever shall we do? Well, notice that these are nodes, and we can always get to them through pointers. So maybe we can iterate through a list using pointers to nodes. Like I'll have a pointer that points here for a second, then I'll have a pointer that points here for a second, and then I'll advance that to point here for a second, and then it's done. Okay, that's the idea. So we're going to have a temporary node. We're going to have a node that tracks where we are. So we'll call it like n or something. N will track the current node I'm looking at. Okay, that's the idea. Let's do this. Alright, so I'm going to make a new file, copy 1, 2 into 123.cpp. Let's do this now. Okay, so we have 1, 2, let's make it 3. So 2's next is now 3, and 3's data is 3, 3's next is null pointer, because it's the end of the list. Okay, and now the last is 3 as well. Okay, so we've made 3 nodes on the heap, we've set their data appropriately, and we've also set their next pointers appropriately. Okay, because the thing after 1 is 2, the thing after 2 is 3, the thing after 3 is nothing. That's the end of the list. Okay? And so first and last are set appropriately. The first node is the 1 node, the last node is the 3 node. Now let's iterate through this list. So we'll keep track of where we are using a node pointer. Okay? It's pointers all the way down in this class now. So here's what we can do. And I'll show it in a while loop and a for loop. The while loop is probably the easiest to start with so that we can wrap our minds around this, but we can easily translate this after I do it into a for loop. Alright, so the idea is we want n, our node n, we'll say node star, and we want it to start right here so we can look at the first node first. So node star n starts out being first. Okay? And once we're done looking at the first node, how do we advance n to the second node? Like that. How do we do that? Well, oh man, inside of this node, I have a next pointer to the next place. I can follow that. I can say n equals n arrow next. Let's advance. Advance is the pointer to next node. And then finally, once we get right here, we'll do our 3, and then we'll advance the n pointer off into null, and that's when we can stop, okay? Okay, so hopefully that makes some sense, but in code it'll make a lot more sense, I think. So we're going to start out our node, equals first, so start iterating from the first node in the list, and then while n is not equal to the null pointer, so while we still have a node to look at, we're going to continue. And let's see, is there a reason why it's confused? Dun dun dun. Node and null pointer. Now I promise that n is a pointer. What have I done wrong? Redefinition of n. Oh, I must have done some n up here. Yes, I did. Okay. So this cannot be here anymore. Let's just get rid of that. How about that now? Okay. So while it's not equal to the null pointer, we're going to iterate. We're going to process the node. And I guess we're just going to print it out, right? That was our goal. Or it can be our goal. We're just going to iterate through it. Let's print it out. Okay, so that's our current node. We're going to print out the data. That will be our definition of processing that node. And then we need to advance the pointer. N equals n arrow next. Okay, so wherever it was, wherever n was, maybe it's here, change it to be the next place. So over here. Okay? Beautiful, beautiful. And that should essentially do it. So let's run this. Let's watch it work and see why it does that. Sure. I'll make that bigger. Okay. And what do you know? We got 1, 2, 3 out of the deal. Isn't that nice? So again, just to go slowly, maybe I'll use a different color. We started n at this node, and we printed out its data. Then we changed n to be whatever its next was. Okay, so then we're pointing to this node. Print out that node's data. Got a 2 now. Then we change n to be its next node. Then we print out the 3, that is its current data. And finally, we change n to be its next node, which is nowhere. It's null. Okay, so we're at the very end, we're setting n. It's like we're setting n to null pointer. Okay, because that is what the next node is. And so that will stop our loop, because that's when we want to stop. And that is the end of that. So I think you can now see how this can be translated pretty easily into a for loop. So let's do the opposite. So not opposite, but same thing. Maybe I'll need 2 new lines. Okay, so here we go. For, what are we going to initialize? Our n equals first, n is not equal to the null pointer, n equals n arrow next. Which is cool, because this is like the I++ of linked lists. Isn't that nice? And then finally, we can do all the same stuff in the body. It's like a separation of concerns. We only have to care about doing the real work now in the body. And so this will do the exact same thing. 1, 2, 3, 1, 2, 3. And up to you, whichever one you prefer. Okay, so this is low-level stuff. We are using a linked list. We've made a linked list data structure. Okay, so nodes. Nodes make up a linked list data structure. Or maybe we can say the linked list data structure. Alright, so we've just made the data structure itself. We had to do a lot of work though to like get everything in the right order. We could make some functions that wrap around this. Better yet, we could make a class that wraps around this and does stuff. And funny, I should mention that because that's the next thing I want to talk about. So we can package up the list data structure in a very nice way that allows us to like interact with it as we would a vector, maybe. Like put something at the end, put something at the front, please. Things like that. So this is a really cool data structure. Let's actually make it easier to use with an abstract data type. So this is just a teaser. We'll talk about implementing it after we talk about C++'s version. But here are some common operations that you might want to do if you had a list ADT. So remember, I don't know where I say this, but I'm going to say it right now, and maybe I'll just repeat myself. Remember that an ADT is just like a cloud. Like I made a list L, I declare it. It just makes some kind of cloud of memory that you can interact with. You can be like, push back. And it'll be like, yes, I now have a thing at the end of my list. If it was empty, now it holds that thing. Then you can be like, push back again. Alright, now it holds 43 as well at the end. And it's building up some kind of idea of a data structure, and you can interact with it using the public member functions. It doesn't have to be implemented in any sane way, though. Okay? So what we could do is, technically, we could make a linked list, or we could do all these operations. We could totally do these operations. Things like this. We could totally do this using vectors. Okay? It would just be horrible in terms of time complexity. And also sometimes space complexity. So technically we could implement a list using vectors. Let's say this here. And I need to resize this so it doesn't go off the screen. Remember that the ADT is just the interface. To some set of operations that act in a way that you know how they should act. Okay? So here are the operations that we could do on a list abstract data type. Insert something to the beginning or the end, so it will make a list, be like, alright, insert 42 at the beginning. Sure. Insert 43 at the beginning. Sure. Insert 44 at the end. Sure. We could do those things. We could make functions. We could make methods that do those things. Get the size. We could keep track of the size, or we could just iterate through our list, boop, 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 and count the number of things. Remove things that are equal to a certain number, like get rid of 42, make the list smaller, make it 43 and 44 after that. Okay? Something like that, like get rid of the 42. Search for 44. And we're going to have to iterate through this list in a linear fashion, aren't we? This should be tabbed over. No, but I guess I can't tab it over. There, that's a tab. Why does search for linked lists have to be linear in terms of the number of things in it? So when I say linear, it's like O of n in terms of n, where n is the size of that list. Okay, it's the length of the list. And let's look at this. Well, the reason is, if you're searching, you got to go through the entire list, and the only way to get to certain places, you can get to the first immediately, you can get to the last place immediately, but anywhere else, you have to just follow a bunch of pointers. You see that? So like if I'm searching for 2, I gotta start from first. Searching for 2, and you can imagine a very long list where this is an issue. So you have to scan through the entire list, even if it's sorted. So search is always going to be linear for this basic kind of linked list data structure. There are fancier versions of linked lists where we can do a sort of binary search, but that is well beyond the scope of this class. Okay? So it has to be linear because we can only follow next pointers. And that T blended in with the P, so let's fix that. There we go. All right. So with that, we've now been introduced to the linked list data structure and the idea of a list ADT. Let's see how C++ does it. Oh man, I should have made this pretty. We'll just do this. We'll do this as we go. This is green. Pretty now. How does the C++ STL do list? And this is known as the standard template library, if you haven't heard of that. Standard template library, or template library, however you want to pronounce it. And we're going to get very, very familiar with these things called templates eventually, but that's what it stands for, and it's just C++'s implementation of general purpose data structure, abstract data types. So let us look through the documentation of the linked list, or the list abstract data type in C++. How does it work? Okay? So here we are. Here is the C++ standard template libraries list. You can go in the containers panel, click list, here we are, and then click list because that's the class we want to look at. All right. So you can read about it if you'd like. It talks about what it does, and we've kind of hinted at this. Constant time insert and erase. What? Isn't that cool? Maybe I should make this larger. There we go. And scrolling down, here's all the stuff that you can do with a list. So once you make a list, look at the constructor, and there's a bunch of different ways you can make a list. Once you make a list, what can we do with it? Well, we can start putting stuff inside. We can push to the end. We can push to the beginning. We can remove from the beginning, remove from the end, things like that. Insert a particular index, erase, so delete an element. We can do some cool stuff, and I encourage you to play around with this stuff. We'll just look at the most simplest stuff at the moment. You can get the first thing, get the last thing. They call it front and back here. Check if it's empty, get the size of this list. Alright, so this is what's going on. So let's start making a list. So our program is going to make a C++ list that holds the Krabby Patty ingredients in order, of course, which are these things. Feel free to rewatch that episode. Alright, so I'm going to work and show you how to make this list with bun, patty, ketchup, mustard, pickles, onions, lettuce, cheese, tomatoes, and bun in that order. So let's build up our list. So then krabbypatty.cpp. So here we go. Include list. So I want to make a list of Krabby Patty ingredients, so I better make a list of strings. And I should also probably include string. Oh, sorry. Hard to type and speak at the same time, I guess. Alright, so we're going to build up our list. So ingredients is a list, and it's initially empty. Alright, so let's add stuff to it. Let's add the bun. We're going to push that using our push operation. And technically, because there's nothing in the list right now, we can push to both the front or the back, and it will end up in the first element, because the beginning is the end. There's nothing there. So ingredients dot push. How about front? Bun. Okay. How about that? Or you know what? Let's mess up. Let's mess up. Let's do. Oops. Let's put the patty first and then fix ourselves, because we can do that with lists. We can add to the front very easily. So, okay, no, it wasn't patty first, it was bun. So let's put that before patty. Yeah? Isn't that nice? And then we can use ketchup, mustard, pickles. Let's just keep going. Oh, but no, that shouldn't be at the front. It should be at the back. Ah. Pickles, onions, lettuce, cheese, tomatoes, and bun. Don't mind me. Mustard, pickles, oops. In that order. Alright, so I think we have a correct list. Now we've built it up, so now the list holds stuff. And we think that it's in the right order. But however shall we print our list? We don't know how to do that yet. Well, one way to do it is, if we go over to our friend the vector, the vector's constructor can take these things called input iterators, first and last, and this has a default value that we don't need to touch. So technically, we could make, and we can get the begin and the end, not that we know what that means yet. We could convert our list to a vector if we wanted to. So we can print it out. Alright, so vector string ingredient vec, let's say, and its constructor, it's going to take ingredients dot begin, ingredients dot end. So it's going to like fill up the vector with all the stuff from the beginning to the end of ingredients. Alright, and then we can print that out for sure. Yeah, so for int I equals 0, I is less than ingred vec dot size I plus plus cout ingred vec at I new line. Alright, this should work. It's just kind of silly. And we'll fix that. Oh no, I saved it as the wrong thing. There we go. And what do you know? We put the bun in the right spot by those two push front calls. Isn't that cool? So we just, in a weird way, we printed out our vector. But we could do better. We can use these things called iterators. So, let's talk about those. We use pointers to move around a linked list. Remember that. We use pointers to go through that stuff. How do you move around through a list itself? Okay, so that's where iterators come into play. And the definition of an iterator is essentially a class that pretends that it's a pointer. It overloads the dereference operator, not the multiplication operator, the dereference operator, the plus plus operator, and other things. Okay? Or the equality operator, and so on and so forth. So that's what list uses. It uses these things called iterators to move through a list. Okay? So you're going to say, that's what dot begin and dot end give you. So L, if it's a list, L dot begin, it gives you back an iterator to the beginning of the list. L dot end. Same for end. And honestly, I think we could also do... no, front and back are the element itself. Yeah. But begin and end are iterators. Okay? That is the idea. So, let's see these in action in a second. But let's first talk about, well, let me show you the example on the internet of using begin and end. Here's like begin. I'd be like, all right, I need an iterator, call it IT. While it's not equal to the end, I'm going to plus it, and I can dereference that IT. And that's how I iterate through things. So why in the world do they pick these kinds of operations and call it this thing called an iterator? You might be asking. And the answer is, it has to do with something called pointer arithmetic. It just so happens that if I had a pointer to an array, like, I don't know, int, of course it's going to do that, ARR equals 345, and then I had int star p is ARR, so p starts at p points, because remember what an array is, to the first element of ARR. And then I can do this. I can say p equals p plus 1. What that does is it advances the pointer to the next int. And this is all quite complicated, and you don't really have to get into this. Feel free to talk to me about it during office hours. It's really an interesting concept that it would be nice if you knew it, so that you knew where people were coming from when they designed all this stuff. But here's the idea. ARR, remember it's secretly a pointer to the first thing in that array. 1, 2, 3, 3, 4, 5. So maybe this is address 100, this is address 104, because these are ints, 108. All right, then P is going to hold the same address as ARR at the beginning, so P is going to hold 100. Let's give it some more room, actually. And it's going to point to that first place as well with this line. But then when we say P plus 1, it actually doesn't change it to be 101. It changes it to be the next int value. It's like the compiler knows better. It changes it to be 104. So you can technically say plus plus p or p plus plus to get to the next element. To the next index, or I guess it really is the next element of that array. You can just say p plus plus all day long, go from here to here, and then eventually you'll hit the end. And that is why the syntax looks the way it does. Okay, so let's now do our example, and we're almost all set. So let's iterate through that list, that original list. We'll use iterators, okay? And it's a special kind of heavily qualified type, which is unfortunate. Here is how you print, how you iterate through a list. You say, I want an iterator. Oh shoot, I'm in vector right now. Sorry. List. Where was I? Begin end, yes. It's essentially all the same stuff. But you say, I have a list. It's a list of ints, and I want an iterator to a list of ints. It's a very complicated type, I know. Call it something, and then you say it starts at the beginning of the list. And I'm going to keep it going while it's not the end, and the end is really one pass to the end. It's not the last element. And then you say plus plus in whichever order. And you say star IT to get the actual value. Okay? So let me walk through that slowly, and we'll print our list. So I'm going to say for. So what is ingredients? It's a list of strings. Okay, so I want a list of strings iterator. I want an iterator to the list of strings. I'll call it IT because that's customary. It starts out at the beginning of the list. And that'll give me an iterator to the beginning. And then I want to keep on iterating while IT is not equal to ingredients.end. So ingredients.end is one past the end of the array. You can think of that, or sorry, of the list. You can think of it the same way for vectors as well. It's always one past. So really it's probably deep down implemented as null, but you get the idea. And then you say IT++ or plus IT, things like that. So now we have an iterator to work with, and we can say star IT gets the string at the current index, or the current, I guess we can call it a node, the iterator is pointing to. Okay, so I can say star IT now, cout, star IT, new line. This is like, pretend it's a pointer, dereference it, get the value there. Okay, so this will get the actual string. Okay. And it'll do the exact same thing. And I guess I needed another new line to have it differentiate. But there it goes. It iterates through the list using these things called iterators. Okay, it's just a fancy class that abstracts away this idea of pointer arithmetic. Okay, and iterating through anything. This works for vectors. The same process works for every C++ container, and you know about vectors already. But we'll learn plenty more. Okay, so that's the idea. We just printed out our Krabby Patty. Now that's a lot of typing. So there's a way to do this faster. C++ 11 and later gives us a way. And this is what the syntax looks like. It's for, and then it's the name of the thing, string element, and then a colon. The colon's important. I'll make that bold if that matters. Inside of the list, my list. And then you can iterate as normal. Element is set to the current element. Alright, so this is just, that colon is beautiful, in essence. What it does is, for string element in my list ingredients, go through please, and cout elem. So it's just going to reset elem each time. It's going to move through that list in order. Okay? It's going to go through ingredients in order. This is called a range-based for loop. Note the colon. Goes through a container in order. And it's no longer necessary to say iterators anymore, it just gets the actual value, so you can use string. And probably a better idea to do things like references, and probably const as well. So we don't want to change anything, we just want to go through it. And oh man, does it also work. That's nice. That's super nice. And maybe one day though, maybe one day you want to use the old version because you want to control things better. Like maybe you want to start from the second element and not the first. And this is a very long type. Let me bring it back down here. Okay, so it's a very long type to type, if that makes sense. we can get rid of that. C++ can infer that type based on the return type of ingredients. .begin. C++ is fancy enough to know that, oh yeah, this is going to return an iterator to a list string. You don't need to type that twice. Auto. That's pretty cool, and that'll work for anything. And again, same stuff. And this will work for any type, actually. If it can infer the thing on the right-hand side of the equality, you can just put auto here. And if you want to make it fancier, like you can always put constant reference around those things. Okay, so auto is when C++ can infer the type. Use auto on the instead of the normal type. And this only works when you're both declaring and initializing, okay? This requires, because you need to give it a thing that it can infer the type of. Okay? That is beautiful, I think. So that is auto for you. And now let's talk about how we might go and implement something like this, C++ list type. We're going to make our own in the lab, and we'll talk about the implementation of all these things in pseudocode. And here I am saying that, oh yes, we could use an array. And let me go to, maybe I can copy in, actually. Copy / Windows Desktop. Starter code, CSCI 41, lab 04, and this is linked list.h to here. All right. This is what you're going to be implementing. You're going to implement a, don't worry that this doesn't compile, but you'll be implementing this linked list ADT. Okay, so probably should have just called it list, but who cares? And here are all the things that you'll implement. Get first, get last, push front, push back, pop front, pop back, size, things like that. So you're going to keep track of nodes. You're going to make them as you need to make them, okay? First, last, update those as necessary. So this is what our list is going to consist of. It's going to consist of, like if I say linked list L, well, L in memory, if it's on the stack, it will hold a first and a last pointer to some place, okay? But really, you could kind of scrap this, and you could really implement it using an array if you really wanted to. You could make it L, like, here's my ARR, that is all the contents of your list, and I will just shuffle things around as necessary, resize ARR as necessary, okay? But we totally would prefer this. We'd prefer to use nodes. Okay, so let's talk about these things. So constructor. How do we implement a constructor for a linked list? I say linked list L, and I have my list L. What should I do for first and last? So we should start out our list empty. Okay, with nothing inside. So that means first and last then should point to nothing. They should be set to the null pointer. And let's do that so I can draw some more. So that's essentially all it means to be a constructor. you're going to set first and last in a special way to make sure that the list is initially empty, because that's what it means to declare a list and have nothing inside. And so that's exactly how it will look. That's our constructor. Not too bad. Okay, insertion. Insertion is interesting because you can push to the front or the end. That's how we're going to do it. Push to front or the back. And let's pretend we have a list again. Right. Let's pretend we had our list L, and then we say L dot push front 42. Something like that. It'll technically be a special type. It'll be this type called point2d that I define in a different file. But you're going to get that thing. It's not a big deal whatever is inside. That's the whole point of templates, by the way. Oh, we'll get into that later. So L.pushFront 42, when L is initially empty, for example, or let's just do the general case. Our list has first and last inside of it, which point to potentially different places. When I push to the front, I need to make a new node with that data value, always. That always needs to happen. Happen on the heap, by the way. And then I need to put it in the first part of the list. Which means that if there's something there already, and this is my new node, like maybe I'm pushing 42, well, its next pointer needs to point here to the old first node, and now first needs to change to be that pointer, okay? To point to the new node. So to point to the old first element, and then we also need to set the new first. Set the first pointer of linked list, the actual class itself, so this first right here, to be the new node because we just pushed it to the front. And there are technical special cases that you should watch out for. For example, if L was initially empty, and you added a new first node, well, you could still follow along the same process. Its next pointer needs to be the old first node, which happened to be null. That works out for you. But the pointers now, first and last, must now both change to be that one node, okay? If the list is initially empty, when you push, I guess I don't need the word initially, then the first and last pointers must change to both point to the one element that's now in the list. Okay, so that's push front, and I think that's where I want to leave us. So we'll come back, talk about push back, which is essentially the reverse, and we'll go from there. So I'll see you next time.